Hello everyone. It seems that a lot of people have difficulty understanding why the horizon is curved on our Earth as soon as you rise above the surface, and technically, although usually undetectable, even from eye height standing at sea level. At first it seems obvious. The Earth is a sphere, close enough anyway, so of course the edge should be curved. But then you start thinking and figure out that, equally obviously, the horizon would be at the same angle all around. So how could it be curved? It should be dead straight. We might call this an optical fallacy. It comes down to projection and perception. First, let's do a little thought experiment. How does it follow that something that is at the same angle all around you would appear straight? Let's look at things that actually are straight. Imagine a piece of straight and perfectly level road, not caring about the surface curvature at the moment, because we will be limiting ourselves to very short distances. Now, say, the stretch of road is 20 meters long, and you are standing in the middle of it at one edge and look towards the opposite edge, as if to cross the street. For the sake of the argument, let's assume your eyes are 2 meters above the ground, and the road is also 2 meters wide. Yes, that is a very tall person and a narrow road, but it makes for nicer numbers. So, looking at the opposite edge, straight ahead, you have to look down by 45 degrees. Now look to the left to see the end of the road, some 10 meters away. According to basic trigonometry, you will have to look down only by about 11 degrees to see that point, which is not really that far away. Now, all points to one side will appear under a different angle, so shouldn't the road appear curved? We all know that it does not. Your senses will tell you quite correctly that it is perfectly straight. Although the human eye has a heavily distorted projection, your whole experience for all your life has trained your visual system to know which projections to your retina, combined with other sensory perceptions, correspond to straight lines, and which correspond to curved lines. These perceptions can be fooled in optical illusions, but for normal situations they work extremely well and are very reliable. For small to moderately large angles of view, our perception agrees very well with what is called a rectilinear projection, in which straight lines are projected onto film or digital sensor as straight lines. It is clear that on a photograph of the street of our thought experiment, we would see the street as a straight line. We could make a large transparency from it, and we would be able to hold it in front of our eyes such that it would align perfectly with reality. A pinhole camera creates a perfect rectilinear projection like that. Things become more complex when we use very large angles of view or curved projection surfaces, but that is beyond the scope of this video. Now imagine fixing the endpoints of our hypothetical street, removing the straight opposite edge, and replacing it with a circle around our feet with a radius of the distance to those endpoints, just over 10 meters away. When we then look at the point of the circle directly ahead of us, it will be the same distance away, and we will have to look down by the same angle as we did for the endpoints to our left and right sides. And yet, it will not appear straight, but we will clearly be able to see and recognize it as an arc. Basic geometry tells us that things work exactly the same if we simply scale up the entire thing, so that we are no longer 2 meters high, but, say, 250,000 meters, and the circle has a radius of 1,800 kilometers instead of 10 meters. These figures correspond to a low Earth orbit, somewhat below the ISS. Using the typical rectilinear projection, straight lines to straight lines, which agrees with human perception, there is no reason why the circle of the horizon should not appear curved to both the human eye and a camera. These pictures visualize a pinhole camera projection surface. Its size is wildly exaggerated, but it is easy to see that it would work exactly the same when sensor width and focal length are scaled down proportionately. While it is true that all rays reaching the pinhole from the horizon are at the same angle, Those striking the projection surface nearer the edges have to travel on for a longer distance and thus rise further before they hit it, in total creating a curved line. I hope this clears up why we would expect to see a curved horizon from higher altitudes, even if the horizon itself is a flat circle. I have published an interactive horizon curvature simulator on GeoGebra for all to play around with. I will link it in the description below. In a future video, I will be talking about the horizon on a flat Earth. It is going to take a bit longer since there is no generally agreed on model of the flat Earth in the first place, so I will have to consider the implications of different sizes, observer positions and finite versus infinite models. That's it for today. Thanks for watching. Subscribe to this channel if you like and spread the word. This video is licensed under a Creative Commons license, Attribution, Non-Commercial, Share-alike 4.0 International. See you next time.
This video is called Google Earth Proves Flat Earth, strangely enough. Okay, going on a cycle ride. The reason I choose cycle ride on Google Earth or Google Maps is because it gives me the elevation, which is what those figures are. Ooh, come out, it's not focusing properly. I'll show you that in a minute anyway. There we are, focusing better. But point being, I've gone on a 600-mile journey, 601 miles from Weymouth to Aberdeen. That's some cycle ride. 601 miles. Now, let's have a look at what we should be looking at. Curvature, Ebbs curve. 600 miles. Let's say 500. Wow, 31 miles of curve, is that? Yeah. 31 miles, 500 miles. We're giving them the benefit of doubt here over 101 miles. But yeah, 500 miles, 31 miles of curve. That's what we should be looking at. Okay, so where are we at here? What we're actually getting is, let's have a look, what's the difference? On the journey, elevation is, I go up 16,322 feet. I come down 16,312 feet. Wow, difference of 10 feet. 10 feet of difference between Weymouth and Aberdeen. 600 miles, 10 feet of difference. And yet that should be 11 miles of curve. 10 feet of difference. And I'm guessing that's the difference of the road height above. That's it. That's just the difference of the road height and nothing else. So, wow. It would seem England from north to south, or Britain from north to south, is flat. Okay. Right, here's our American journey now. We're going from San Francisco to New York, which is Battery Chamberlain Road to North Road. Zoom in quickly if I can. San Francisco location. From the west coast all the way across the east coast to New York. I think this is the Hamptons, quite a posh part. Going right to a point again by near the sea called North Road by the look of it. Yeah, Montauk Point Lighthouse. Anyway, journey is 3,350 miles. Elevation up 63,150 feet. Down 63,146 feet. Total difference is 4 feet difference from coast to coast. And I'm guessing that is in the difference of the height of the roads. 4 feet difference. 3,350 miles. The curve chart now tells us what we should have been looking at. Over 1,000 miles of curve. At 3,000 miles, you're looking at 1,375 miles of curve or drop. And what was it? 4 feet difference. 4 feet difference. It's flat. It's fucking flat.